2, guys. Alright, so just as I was saying, so if we have a function that is one-to-one, or passes the horizontal line test, how do we find its inverse? Okay, and that's what we're going to look at now. Well, we've got a 4-step process to do that. First thing we need to do, though, is verify that it is actually one-to-one. Okay, but I can tell you, I think all of the ones in your homework for which you have to find the inverse, I think that they're all one-to-one. But technically what you would do is graph the function, make sure it passes the horizontal line test, and then proceed. Okay. Alright, so this is the 4-step process right here. So once you know that the function is one-to-one, you're going to replace f of x with y, because we know f of x, the function value, is the same as y. And then you're going to swap the x and the y. This creates your inverse relation. Okay, and then you want to solve it for y. So in other words, you're not only creating the inverse relation, you want to rewrite it as a function of x. You know, y equals whatever x. And then finally you replace y with this inverse notation. Okay, so this inverse function will also be a function of x. Alright, so let's try one here. Example 3 says, for the following function, determine if it's one-to-one, and if it is, we want to find its inverse. Okay, well this is a linear function, so it is definitely one-to-one. Okay, so then I can proceed with that 4-step process. I'm going to replace f of x with y. I'll just rewrite it. Okay, and then I'm going to swap x and y. And once you've done that, you've really created the inverse relation. Okay, what we want to do is rewrite this as a function of x, so we want to solve it for y. And it's this 3rd step where most of your work comes in. Okay, so if I'm trying to solve this for y, I need to add 3 to both sides of my equation. Okay, and this will give me 2y is equal to x plus 3. And then I'm going to divide both sides by 2. Now I've got to divide the entire left side by 2, so I have to write it like this. And so on the right hand side, my 2's divide out. I get y is equal to x plus 3 over 2. And this is my inverse. Okay? And my last step is I want to write it using that notation. So it's a function of x now. So I express it by saying f inverse of x is equal to x plus 3 over 2. And this is actually another linear function. It's the same as 1/2 x plus 3/2. Okay. Anyway, one other thing I want you to notice. You essentially create the inverse by performing all these inverse operations. Okay, so instead of subtracting 3, we add 3 to both sides. Instead of multiplying by 2, we divide by 2. Okay, and so that's how we came up with this. That's what I did up here in my head. I knew that this, whenever you plug something into this function, what it does is it multiplies it by 2 and then adds 1. So if I go in the reverse order, I need to take the 1 away and then divide the whole thing by 2 to undo what my original function did. Okay. And then if you want, you could graph f and f inverse, and you'll see that symmetry again. Okay, we'll graph some of these here in a minute. Alright, let's go to example 4. And then here, I'm just saying that when you do graph both of them, you'll see symmetry with respect to that line, y equals x. Alright, so for this function, determine if it's one-to-one. And if it is one-to-one, we want to find its inverse. But we could graph this one real quick just to make sure. It's a rational function, isn't it? 2 over x plus 3. Let me Okay, well, just 2 over x plus 3. Okay, so we see that typical rational behavior, right? There's a vertical asymptote, there's a horizontal asymptote, but this is 1 to 1. This would pass the horizontal line test. Now I know it starts to level out over here, but remember, this is always decreasing. This function decreases forever. It just never actually reaches the x-axis, because that's where our horizontal asymptote is. So this is a 1-to-1 function. Okay, so then we can go about finding its inverse. So I'm going to do it the same way. I'm going to replace f of x with y. Okay. I'm going to swap my x and y's. So I have x equals 2 over y plus 3. And then I'm going to solve this for y. Now because the y is down here in the denominator, guys, I need to get it out of the denominator. So what I'm going to do is multiply both sides of this equation by this denominator. In other words, multiplying both sides by y plus 3. We saw something similar to this in one of the examples in 8.5. So the reason for this is because on the right hand side these binomials will divide out. Okay. And so I'll just be left with 2 equals. Over here we would distribute the x to both of those terms. So you would get, you could write yx, but I'm going to write xy, and then plus 3x. Okay. And now what I've got to do is try to get my y term by itself, so that I can eventually solve this equation for y. So I'm going to subtract 3x from both sides. And this will leave me with xy equals 2 minus 3x. And then if I'm trying to solve this for y, the y is getting multiplied by x, so I'll divide both sides by x. But again, remember, on your right-hand side, because you have 2 terms, you've got to divide the whole thing by x. So on the left-hand side, the x's divide out, and we're left with y is equal to 2 minus 3x over x. And then finally, I can rewrite this using that inverse function notation. So f inverse of x is equal to 2 minus 3x over x. Okay. Now I want to show you graphically that if we graph f and its inverse, we'll see that symmetry. We'll come back to Desmos. I've already got f graphed in there. Now I'm going to graph f inverse, which was, I already forgot what it was, 2 minus 3x. 2 minus 3x over x. Okay. Now you may be looking at this and like, wow, what's going on here? There's no symmetry. But when I type in this line, y equals x, there you can see. You can see that this piece right here in red, if you flip it along this black line, will end up being this purple piece down here. Okay. In other words, guys, what's happening, the coordinates of the points that make up our original function, their x's and y's are trading places. And those become the points that make up our function, our inverse function here in purple. Okay. So we do see some symmetry. You can kind of zoom out and see that. So anyway. Alright, so let's look at example 5. Same thing here. Okay. This is a cubic function. Let's go ahead and graph it just to verify that it is in fact 1 to 1. I think it is x cubed plus 2. Let me look. Yeah, x cubed plus 2. This is 1 to 1. You may think, well, isn't it kind of horizontal here? But it's actually not. The more you zoom in, the more you'll see that it's actually increasing. See? I know it looks horizontal here, but it's actually increasing, guys. And so, because of that, this is a strictly increasing function, which means it will pass the horizontal line test, so it has an inverse. It's a function, and that's what we're going to find. Alright, so we'll do it the same way. Replace f of x with y. Swap our x's and y's and solve it for y. And so in solving it for y, we're performing all the inverse operations. So that's what creates the inverse function. Alright, well, if I'm solving this for y, I need to subtract 2 from both sides. Okay, so this will leave me that y cubed is equal to x minus 2. And then, how do we get the y by itself if it's being cubed? Well, what's the inverse operator? The inverse of cubing something is taking the cube root of it. So if I take the cube root of y cubed, I've got to do it on both sides. The cube root of y cubed is just y. So we get this cubic function, okay? And lastly, I'll rewrite it using the inverse notation. F inverse of x is the cube root of x minus 2. Now let's graph these two. I've already got f in there graphed. So now I want to graph its inverse, the cube root of x minus 2. So we'll say y equals I'm not actually sure how to do a cube root in Desmos. There we go. I had to you have to type in just sort of the initials, well, not initials, but a few letters from the word cube root that distinctly kind of identifies it. So a square root, it's SQ for square and then RT for root. So for cube root, it's CB for cube and then RT for root. Okay, and then we can type in here x minus 2. And look, you can see that symmetry. See? Another thing, guys, with these inverse functions, wherever one function crosses the y-axis right here at 2, that's where it'll cross the x-axis. See, 2, 0, and then over here, this point, 0, 2. Basically what's happening is the domain of one function is becoming the range of the other, and vice versa. And then we can graph that line of symmetry too if you want. And it just cuts those in two mirror images or reflections, doesn't it? Okay, it's a pretty shape. Geometrically looks kind of like a heart, maybe, part of a heart. Alright. Okay, well, I think we've got one more, actually, well, a couple more to do. Okay. So many times a function may only be one-to-one if we restrict its domain. So think about this function right here, x squared minus 2. Let's graph it. I talked about this earlier, but not in great depth. X squared minus 2. Alright, so we know that it's quadratic, so it's going to be a parabola, but you can see it is not one-to-one because it doesn't pass the horizontal line test. However, if we restrict its domain, and I'm not sure how to do that in here. No, this is not working. I was trying to restrict this domain for only values of x that are positive or 0. If I did restrict this domain, guys, we would only get the right-hand piece, or you could restrict it such that you get just the left-hand piece. So if we do restrict its domain, then it is going to be a one-to-one function. You end up with just either the left-hand piece or the right-hand piece, okay? And that's actually what's happened with example 6. So look at example 6 here. This is a quadratic function, okay? So we know by itself it's not one-to-one. However, if we restrict its domain, if we consider only values of x that are greater than or equal to 0, or in other words, the right-hand side, then it is one-to-one, and we can find its inverse, okay? And so that's what we're going to do. So you find the inverse the same way. Change the f of x to y, 3x squared plus 1, okay? You swap your x's and y's, and then you solve it for y. Well, one's been done up here for you, okay? See this one? And the issue is that whenever you get that y by itself, you have to take the square root of both sides. But when you do that, you get a positive and a negative. And so what we have going on here is we have two different outputs for one input. So that's why, unless we restrict the domain, the inverse is not a function, right? But by restricting the domain, you're basically restricting the range. Okay, so like in this example here, if we just let x, if we restrict x to be greater than or equal to 0, then the range of this function will be greater than or equal to 0, or in other words, all the positive square roots and not the negative. Okay, and that's kind of what we're doing here. All right, well, let's actually solve this for y first. I'm going to subtract 1 from both sides. So I'll get 3y squared is equal to x minus 1. And I'll divide both sides by 3. Oops. And I'm going to reverse the order here. This will leave me with y squared is equal to x minus 1 all over 3. But this is where I have to take the square root of both sides, and when I have to put plus minus. Okay, so I get y is equal to positive and negative square root of x minus 1 over 3. Well, for this to be a function, we can't be getting two different outputs. So which one is it going to be? Is it going to be the positives or the negatives? Well, it all has to do with that domain restriction. So if you're restricting the domain to just the positives and 0, that means that for your inverse function, the outputs are only going to be positive or 0. So in other words, f inverse of x can only be the positives. Okay, so you don't have to write the negative. And you can see this. If I graph this in Desmos, the square root of x minus 1 plus 3. Well, actually, I'll need to graph this original. 3x squared plus 1. Let's do this. 3x squared plus 1. Okay, so we're restricting the domain, so pretend that the left-hand side is not there, is missing. And then our inverse was the square root of x minus 1 divided by 3. Okay. And you may think, well, these don't look symmetric. But if you disregard the left-hand side of the red function here, then they are. Okay. Because this point right here, 0, 1, is this point over here. Oops. 1, 0. See that? And the same thing for every other point on this right-hand side. If you swap its x and y coordinates, it ends up being over here, making up the graph of this inverse square root function. Okay? So anyway, now if we had restricted the domain to values of x that were less than or equal to 0, then over here we would have disregarded the positive outputs and kept the negative outputs. Okay. So anyway, all right. Well, let's look at one more. Example 7. So for this function, determine if it's 1 to 1, and if it is, find its inverse. Well, this is going to be a 1 to 1 function. It's the square root of x plus 2. You remember your transformations, it's just being shifted to the left 2 places, right? So typically starts at the origin. So here it is. It's like half of a sideways parabola. All right, so we want to find its inverse. So y equals the square root of x plus 2. Now I'm going to swap my x and y's. Okay. And then I need to solve it for y. But the y is trapped under the square root. So how can we get access to it? Well, we do the inverse. We square both sides. When you square a square root, you end up with just whatever's underneath it. Okay, and then we square the x. And then if I solve this for y, I'm going to subtract 2 from both sides, so I get y is equal to x squared minus 2. Okay, now this is quadratic. Now what I need to do here, though, is I need to make a restriction on its domain. And to do that, you have to think about, well, what was the range of this function? The range, or the y's, of this function are greater than or equal to 0. So that needs to be my restriction on the x's of this function. Okay. X squared minus 2, but we only want to consider values of x that are greater than or equal to 0. Because remember, the domain and the range are opposites for these inverse functions. So if the range of my original function is just 0 and all the positive real numbers, then that has to be the domain for my inverse function. Okay. So in other words, you could graph this, you'll get a parabola, but you're only keeping the right-hand piece of it. X squared minus 2. Let's do this real quick. Okay. So you can think about, if you're just keeping the right-hand piece in black, you throw this piece away, and you need to figure out how to restrict that domain. Decimals. But if I type in there our line of symmetry, okay, remember, ignore this piece right here, the left-hand piece. Then we would see that symmetry. So see here, this point negative 2 comma 0. This point down here, 0 comma negative 2. Same thing for all these others. This point right here where it crosses the x-axis corresponds to this point over here where it crosses the y-axis. So anyway, alright guys, well I tried to give you an example that corresponds to each of those different types of homework problems that you're going to see for this section. Alright, so in the next section, 9.3, we're going to look at a totally different type of function that we have not seen in this class. It's called an exponential function. And it's good for modeling a lot of different types of behavior that I'll mention when we get there.